society. No worries. Yes, great. Whether it's through sort of prediction tasks where basically you want to learn a function like a model that will be able to get a new input like an X-ray and predict whether it has heart disease or not. We've seen breakthroughs in this area, protein structure, or whether it's inference. For example, you have a specific parameter you want to learn about your population, like their average income or like the correlation between income and education. And again, we've seen breakthroughs there as well. In any case, the standard pipeline goes like this. You have some population that you care about, some population D, you want to learn something about that. You draw a data set X, IID, from that population. You give it to your algorithm, and you hope the algorithm will give you an output that would be useful for the population. And so you want to perform well on the population, and you're using the training dataset X only as a proxy to the population. However, what does turn out to be the case often is that the performance of these systems is sort of unreliable. And the thing I want to focus on is that the outputs are brittle to changes in the input. And why is that a problem? One example I'll highlight is the first one over here where there were some X-rays. The name of the patient was in a single one of those data points, like a huge data set, a single one of those had the name of the patient. Anyone after that whose name was left on the X-ray was predicted to have like two more, because it's a feature that was just on one single example, but still the model decided it's important. So the overall thing that we see happening is that the outputs of these data-driven systems are overly tailored to the specific input that they have, the training data set. And so although this is not the only reason they misbehave, it's one thing that I want to focus on. And so we would like ideally to get algorithms that do not have this effect. So we would like to design stable algorithms. And by stable, this could mean a lot of things. So there's a bunch of risks that you could think about that fall into this category, like data poisoning attacks. You change a small portion of your input and the output diverges a lot. Information leakage, again, this is the same effect. You can tell from the output that there was a small change in the input, and that's a problem for privacy. Overfitting, the output only works well on the specific training data set in your input, not other data sets. Irreproducibility, all of these things. For all of these things, there's actually a formal algorithmic stability notion that tells you how to defend against it. So there's robustness to data corruptions, differential privacy, generalization conditions, replicability. So for all these things, there's a formal notion that tells us that if the algorithm satisfies something like this, then it defends against the risk on this side. And so on a high level, what I want is to find good principles for designing algorithms that are stable in some of the senses that we have here. So they're stable enough to mitigate the risks, but at the same time, they're efficient in their use of other resources so that they're practical. I will focus on a few of those things, but I think the thesis that I want to pass throughout the talk is that it's particularly useful to think of them as a unifying theme. It's good to try to, borrow things from one to the other to design algorithms that there's two things that could happen. One is you could find techniques that actually help from one field to another. And the second thing is that you could be ending up finding techniques that actually achieve all of these things together, which are all desiderata that we want from machine learning systems.
So is there a single definition that generalizes all of them? Or?
I would say algorithmic stability is, you tell me what changes in the data means and what closeness in the outputs means, and then you could say everything falls into this category. I'm saying it's a family of definitions where some change in the data, you can tell me what you think appropriate change in the data should be, leads to two outputs, which should be close. They shouldn't diverge too much. And again, you should tell me what close means. And if you define these two things, then you get all these things that are here and others possibly. So all that said, my work is mostly on differential privacy, and I'll tell you why I think sort of this is one of the hardest ones to achieve. But again, I will highlight in the middle and towards the end some connections to both robustness to data corruptions and generalization. And this is an area where I've done some work as well, and I'm still interested in, so happy to talk about. Okay. So let's start. Well, for the main part of the talk, we'll focus on differentially private mean estimation of Gaussians. We'll talk about this problem, and we'll try to highlight the challenges that exist in general in the area of differentially private statistics, and basically discuss the connections between privacy and robustness that helped us solve this problem. Okay. So focusing on privacy now. The scientific community has demonstrated in a bunch of ways from pretty early on that sort of privacy is really hard to achieve with ad hoc methods. So anonymizing the data is not enough. You can actually reconstruct the whole database by just looking at aggregate statistics that were drawn from this database. One of the simplest ones is membership inference. You can tell if someone was in the dataset or not. And that on its own is a privacy violation. There are many datasets in which you wouldn't want someone to know that you're in, possibly, if you start thinking about it. So we've known that there are all these attacks for a while, and there are laws that say that none of these things should happen. People shouldn't be able to tell if you're in a data set or not, singling you out, and so on, such as GDPR, California Rights Privacy Act, the privacy mandate that the US Census has. So there are a bunch of laws in place, but then the question is, okay, we have all these attacks. Let's say you build a system that defends against the attacks that we know. After how many attacks that have failed, or like which attacks do you think you're safe? The system is private and you can just release the information. And enter differential privacy, which is a rigorous standard that provides the language that helps us measure privacy leakage of data-driven systems. It's been adopted quite widely in industry and government, and it protects against all the attacks that we saw before and beyond. Starting actually is pretty much tailored to the membership inference attacks, and I think we'll see that when we see the definition right away. But basically, it says that the membership inference attack should fail, at least. And then all the others that are stronger will fail. Okay. Here's the definition. It was introduced in 2006. And on a high level, it says that if I change one person's data in the data set, anyone who sees the output, no matter what other side information they have, how powerful a compute they have, shouldn't be able to tell that I changed this data point in the input. So more formally, an algorithm is epsilon delta differentially private. Epsilon delta are the privacy parameters. If for any two data sets that are neighboring that differ on exactly one data point, for any output that you see, the probability that you see that output under dataset X is close to the probability that you see the same output under dataset X prime. And what is close? It's this e to the epsilon times the other probability plus delta definition. And so we think of epsilon as a small constant, think of it as 0.1, and delta should be really, really small, because imagine if delta was 1, this would be satisfied the whole time, right? So we want non-trivial guarantees, and delta you should think is really small, like at least 1 over the size of the data set. Any questions about the definition? Great. Okay. So a challenge in general in this area is the following. So the privacy definition is worst case, right? We said this should hold for any two pairs of data sets that differ on one data point. I'm making no assumptions about the data set. As this is on purpose. I want to be able to protect any data without especially outliers. So I don't want to make assumptions on the two neighboring data sets. So privacy is a worst case guarantee. So this means that this is supposed to show a huge space, this box over here. So this means that even if my data lie in a really small space over there in this ball, I should be able to protect against a change of a data point that's really far. So if the data set is this versus the data set is this removed and this added, no one should be able to tell from the output that this change happened. At the same time, I do want accuracy to be as good as possible. And the challenge is finding algorithms that satisfy this worst case privacy guarantee, but their accuracy or their error adapts to the instance. So there are instances where we can achieve much better error, and we want to find these algorithms that could take advantage of the specific data sets or data distributions that we have to get better error while satisfying privacy without these assumptions always. A really good test case for this kind of thing is the problem of Gaussian mean estimation. Why? Gaussian data are really well concentrated. So they, with very high probability, they fall within a ball of, sorry, I'm gonna try to figure this out once. And, oh no, okay, this is fine. Fall within sort of the ellipsoid of their covariance matrix with very high probability. What does this mean? That it's going to have, in any direction, the data will fall within, 2 standard deviations from the mean in that direction. So they will be very highly concentrated, but at the same time, Gaussian data are infinite. So again, this doesn't look infinite, but it's supposed to be, think of it as a huge space that we don't want anything to do with. So we want this to think of this R as being basically infinity. And so the problem is the following. You have this huge space. Well, let's assume that all the data will lie in this high dimensional box, but again, we'll think of it as really big. We want to find a private algorithm that, however, if the data are drawn from a Gaussian distribution like this, that's well concentrated, gives us really good error. This is just the same problem. So more formally, we have n samples drawn from a Gaussian distribution. We don't know the mean, we don't know the covariance. We want to find an estimator mu hat that is private, but also has good error. So how do we measure the error? It's with respect to this Mahalanobis distance over here. So we want error alpha with respect to this Mahalanobis loss, which basically says that I want the error to have the shape of the covariance matrix, to scale with the covariance matrix. So if the error, if the error was the Euclidean distance, just L2 norm, then I would want a mu hat that falls within a ball of radius alpha from the true mean. What I want now is this change. So I want the mu hat to fall within this ellipsoid that has the shape of the covariance matrix. So this is a pretty natural accuracy metric because it's a fine invariant. And basically, what does it say? It says that in the directions where I have larger variance, like the inherent uncertainty of the distribution is larger, I'm allowed more error. In the directions that have smaller variance, I want smaller error. And so the error in any direction is basically alpha times the standard deviation in this direction.
Is this definition specific to Gaussian mean estimation?
No. But the results that I will talk about require a Gaussian or just symmetric distribution. We'll focus on Gaussians just for the fact that they're well concentrated with high probability. Okay, so this is the problem. And without privacy, it's very easy to get an estimator. You just average the points in your data set. This is the empirical mean. And the empirical mean gets you this accuracy with a number of samples that scales as d, the dimension, over alpha squared, the accuracy target. Okay, this is the best we can hope for, right? Without privacy, that's what you can do. What we really want is something that gets as close to this as possible. Note, the unbounded space R, where the data might lie, is nowhere here in the sample complexity. Okay. The first thing you might try, and standard mechanisms in differential privacy do that a lot, is clip the data set to whatever you can assume, like whatever space you think the data will lie, like where you're sure, and then add noise. So how much noise will you add? This depends on the global sensitivity, which is a notion that's very central in differential privacy. And it's basically saying the global sensitivity of a function is how much does the function move if I change one data point. And it is central because that's the thing that I'm going to try to hide with my randomness, with the noise that I'm going to be adding. So the empirical mean specifically, how much will it move? Well, it can move like across the diagonal. I think I have this. Okay, across the diagonal. And so it will move by 2r square root d over n. This is very sensitive. So to satisfy differential privacy, I'm telling you, this is not something we're showing. You can add Gaussian noise and basically sample a point that has a center in the empirical mean and noise large enough to cover that sensitivity. And once you do that, this is actually epsilon delta differentially private. So this would be an approach that we'd like, except we've added a bunch of noise there. So in order to achieve accuracy alpha, the number of samples we need, like you see, n is here. So as n grows, the accuracy gets better. So the number of samples we'd need is d times r times like some square root log 1 over delta term over epsilon alpha. So the bad thing about this is r. Again, without privacy, this huge space where worst case data might lie isn't in the sample complexity. But with this approach, it does show up. So what we want is to get rid of this dependence, to essentially have a sample complexity that doesn't depend at all on like the worst case data sets that we consider for privacy, but only on the good data sets that we consider for accuracy. And there was a lot of effort to get to the optimal sample complexity for this problem. But maybe the milestones where if you know the covariance matrix, we figured out a way to do this without any dependence on R. And then if you don't know the covariance matrix, there are two approaches where you either get a worse dependence on the dimensionality, which we also think is high, so we don't like this, or a log R dependence, still better than R, but R is still there. And this is the algorithm that I will tell you about, which achieves the optimal sample complexity, which doesn't depend on R at all. And it's quite close to the non-private one.
And what if bounded or not bounded parameters? Or maybe you were going to say that.
No, it's a great question. So I suppose it just means that, so I'm hiding another parameter here, the condition number of the covariance matrix, but these approaches depend even logarithmically on these things like the condition number and R. So these parameters have to sort of be bounded or small for this to make sense. The dependence, exactly. With the other things are independent. Any other questions? So what? Yes?
I think you're gonna go. I still didn't catch the assumption that you're still making here. Whether it's part of the other ones too or something. But we'll talk about it.
We're making no assumptions for privacy. We want a private algorithm, but it will be accurate only for Gaussian data. But we don't need the mean and the covariance to satisfy any assumptions. Whereas here, because the sample complexity depends on bounds of the covariance and the mean, this would only work for things where R and the condition number are small. So what we wanted to get is the optimal sample complexity that is independent of these parameters. Yes, so we'll talk about the two ideas that go into this algorithm, and then at the end, sort of an underlying thing that that maybe will shed some light on why this works in general for statistical estimation. Okay, again, this is our goal. We'll show that there exists an epsilon delta differentially private estimator, which given this number of samples returns an estimate mu hat, which has accuracy alpha with high probability. So this is the optimal sample complexity. And the main challenge here is that we should add noise that's somehow proportional to the covariance, because we want this error here to be in Mahalanobis distance. But we don't know the covariance matrix, and we don't want to estimate the covariance matrix privately because this requires more samples. Okay. So first idea, the empirical mean was too sensitive, right? So, sorry, this was the question. The empirical mean was too sensitive. There's something else called the Tukey median, which is not as much for Gaussians. So let's define the Tukey median. First, we'll define the Tukey depth. For any point in the space, y, the Tukey depth of that point with respect to a data set x is basically how central y is to the data set x. And so it's formally defined by the minimum number of samples that is left on either side of any half space that goes through y. One dimension, any half space that goes through the blue point leaves at least 2 points on either side. Any half space that goes through the green point leaves at least 4 points on either side. So half of the data set. The point with the highest Tukey depth is called the Tukey median, and in one dimension is just the median. So the Tukey median is any point that leaves half of the data set on either side. And so it has Tukey depth n over 2. So, Tukey median is this. The Tukey depth just generalizes the idea of quantiles, not just the median, just all quantiles in high dimensions. So in this two-dimensional example, the red point, no matter how I turn this half space, will leave at least 2 points on either side of the half space. And so its Tukey depth will be 2. This was the smallest. Okay, so high Tukey depth means close to the center of the data set. Okay. It's a well-known robust estimator of the Gaussian mean. And what's good about it is that basically points with high Tukey depth follow the Mahalanobis loss shape. So this is a set of points that has Tukey depth at least n over 3, n over 4, n over 5. The highest Tukey depth is at the center. The lower Tukey depth is is as we grow on the sides. And the point is that any point y that has high Tukey depth has small Mahalanobis distance from the true mean of the Gaussian distribution. So it basically does the thing on its own. So what we really want is to sample a point with high Tukey depth. And I won't tell you why this is private, but we'll basically do it privately. All we'll do is just use a standard mechanism that's called the exponential mechanism. But just trust me that this does satisfy differential privacy. So what it does is sample a point y with probability that's sort of higher if the Tukey depth of that point is higher. So with high probability, this thing will sample a point with high Tukey depth. And this is great because this is going to be close to the true mean with respect to the Mahalanobis loss. I haven't told you something, which is where will I sample from? Like, what is the space on which I will assign probabilities according to this on points y? One idea is the big high-dimensional box where I assume the data. And this is what got us to this log R sample complexity that we saw before. What is the problem? It's just that this wastes probability mass on points that could be really far from the true mean. It does assign probability mass to any point in this high-dimensional box. And so a lot of these points will be sampled with some probability, even though they're really far from the mean. I want to sample from a smaller set, ideally. I want to lose the dependence on R. Absolutely.
A lot of them be sampled?
They have a very low, yes, but this is at least gets you the log R dependence. It's not an R dependence, but still the normalizing factor will make everything smaller.
But hold on.
Yes.
So when you sample in the exponential mechanism, you have to sample, you have to know upfront, right, the number of samples that you're going to be making.
We're assuming the continuous thing, yes, but you need to know. You have to sample from some bounded space.
And you end up in the right place or in the wrong place, and you're going to assign the probabilities of sampling the actual result of the exponential mechanism according to these Tukey depth things.
Yes.
Okay.
So with high probability, it will still output a point with high Tukey depth.
Yeah.
But the point is that because we're assigning probability to this huge space, we're sort of wasting it by reducing everyone's probability of being sampled. So the second idea of this algorithm is to sample from a smaller space. And how will I choose this smaller, better space? I'm going to look at the data. So I'm going to sample from a restricted space of points that already have large Tukey depth. So they're already pretty good points with respect to the error that I want. So we call this the restricted exponential mechanism. And basically, we're going to be sampling points only over a space of points that has at least n/4 Tukey depth. So remember, we want n/2 is the median, is the best we can get. You can pick, it doesn't have to be 4, but we already sample from a space that has some high Tukey depth. Second problem, this might not be private now. So under one data set, you sample from this space that I drew here. Under another data set, you change one data point, and the set of points that have Tukey depth, at least n/4 under x prime, might be different from x. So there's this space of points here, the red points, that under one data set have 0 probability of being output, and under the other data set have some probability of being output. So I want to make sure that this thing will be small enough. The probability that I will assign to point like these will be small. How will I make sure that this is the case? Again, I will not tell you why this is private, but I will tell you the idea is to have a pre-processing check. This is a brute force check. It doesn't, it's not really algorithmic until later that we figured out a way to do this, but basically it says, check if your dataset X is far from being unsafe, meaning check that your dataset X will have, for any neighbor, a very small set of points in the red area.
If any neighbor means one point is changed, but the values that point can be changed to are
arbitrary.
Very many. So how can you do a brute force check if there's so many of them?
The original algorithm was more like a proof of concept information theoretically what you can do. And if you want to discretize the space in the R space and look over like n times d to the d, I don't know.
So you
points
obtain
you
the
can.
pre-processing phase to do work proportional to R. Yeah.
The
'Cause
running
you were
time
trying to remove the R.
from the sample complexity.
Oh, I see.
This will,
I
I will
you're
pay in
trading off
running
the
time.
sample complexity to the running time.
Mhm.
I see.
But
I
we
see,
did
I
come
see.
up with another idea quite recently that makes this step better. You need to compute the volumes of all Tukey level sets, which is again, if you want to do it exactly, it's exponential time, but it's n to the d and it's not r.
I see.
So you can improve this, but great.
But I still need
Yes.
why
It's
this
private.
Initial thing, this step is private.
I didn't tell you, that's why. We use a proposed test release to check privately that the data set is far from the unsafe area. Okay, there's one last thing to figure out, not an idea. This is the algorithm, I promise I'm done.
Just
Yes,
one second. And
absolutely.
the sample complexity of that,
Yes,
you will include it in the eventual outcome.
everything. Yes, yes, yes. Mhm.
Together.
Everything together. It's log 1 over delta over epsilon. That's all the number of samples I need to figure out if it's far from unsafe. So it's not even dependent on D. Okay. Last thing, this whole thing is private. Is it accurate? We know that this is accurate enough. It's not wasting probability mass. It's sampling a point with high Tukey depth. But I added a pre-processing check, and I want to make sure that I'm not going to fail it all the time. So will Gaussian datasets pass the pre-processing check? Again, what is it checking for? It's what it wants to make sure that if you have a Gaussian dataset and you change one point, the set of points that have a certain Tukey depth will not change too much. The red area is not too big. So just an illustration, we'll go to one dimension, and the reason this whole thing works is because Tukey depth is robust. So you have one dimension, you have a Gaussian. These are all the set of points that have Tukey depth at least n over 4 with respect to the data set. So any point I pick, it leaves at least 2 points on either side. Okay? Any point in this light blue area leaves at least 2 points on either side. I move 1 point and I take it really far. The good thing about the Gaussian data set is that it's well concentrated though. And so even though I moved this point really far, I have the next point really close. And so the area of points that has Tukey depth, at least 2, doesn't move too much. It's only this space here, a small space, that just captures the next data points from the next data point from the blue that I had here. And so just as an illustration, it's not a proof, but the fact that Tukey depth is robust to a change of a data point, you can move it arbitrarily far, but because Gaussians are well concentrated, the space of points that have high Tukey depth with respect to the Gaussian dataset will not move too much. We'll stay on this just a bit.
Basically,
Yes.
Smooth sensitivity, if you could calculate it, would be low, but
Exactly.
global sensitivity of this thing is high.
Yes.
I think the key point.
Exactly.
And there is no way to compute it easily. Then you would use.
We can't, I guess we can't take advantage of it directly with the framework that they have. Okay. This was the whole thing. First, we found that the restricted exponential mechanism with the Tukey depth score function is epsilon delta differentially private, and it only needs basically d over alpha squared, which is the non-private number of samples that I need for the Gaussian to concentrate enough, d over alpha epsilon for the exponential mechanism to do its job and draw a point with high Tukey depth, and log 1 over delta over epsilon for the first pre-processing check. So why did I say that the Gaussian mean is a good test case? It's not the only instance, but the mechanism that we came up for this problem was later used for other statistical tasks. Again, the restricted exponential mechanism, the main idea is you only search over a space of like good points already. And this was used for other like linear regression, PCA, covariance estimation in Frobenius norm and spectral norm, like in other things, under different assumptions, like sub-Gaussian distributions, heavy-tailed, and others. And we got the optimal differentially private statistical estimators for these tasks by using this general approach. Tukey depth has to change. This is not the right thing for all these things, but the restricted exponential mechanism was the thing that was used. I want to take a really small detour before finishing to say we saw a little bit that robustness helped in this approach. And I just want, maybe if you take away one thing is that this is not an accident. And going back to the fact that I mentioned in the beginning, I really like thinking about these things as sort of stability notions that help each other, and we should borrow things from one another. There's an underlying reason why it helped. There's a long history between differential privacy and robustness. Maybe I would say it started from proposed test release in 2009, where Cynthia Dwork and Jinglei showed that, well, hinted to that, by several examples, that robust statistical estimators present an excellent starting point for differentially private estimators. This is not proof, it's just saying it's a good idea to start with a robust estimator for the same problem when you try to find a private one. And including our work and a bunch of other works that came up with optimal differentially private statistical estimators did the same thing. These are ad hoc approaches. It's not a standard way to do this, but starting from a robust estimator and trying to privatize it the same way we did with Tukey median, Tukey depth, and try to privatize it in the example before. And so the main punchline that I want to tell you that this is not an accident, and that actually you can always transform any robust estimator into a differentially private one, and vice versa, but that we kind of knew from 2009 and with other works earlier, with minimal overhead in sample complexity. And the overhead is small enough so that basically this result implies that in low dimensions, robustness and privacy are equivalent in the sense that you need the same number of samples to satisfy them for a certain level of robustness, a prescribed level of robustness, and a prescribed level of privacy. So there's an equality that says, if you set the level of privacy to be this much with respect to the level of robustness, or the opposite, the satisfying robustness and privacy has the same cost in sample complexity. We came up with optimal differentially private estimators with this black box transformation just by borrowing the results from robust statistics. We came up with the first polynomial time differentially private estimators for some tasks. And we imported information computational gaps. So if robust statistics say a certain problem can't be done in polynomial time unless you have a bunch of samples, then it can't be done under privacy in polynomial time unless you have a bunch of samples, and the other way around. So on a high level, I think it's a connection that's good to keep in mind, and at least it gives you a first approach to see what sample complexity you can hope for a problem in differential privacy. Just looking at the robust statistics literature and figuring out the relevant thing. Okay, any questions so far? I think we're sort of wrapping up. I'll tell you a little bit about other connections that I find interesting in other areas, but this is the differential privacy, the main technical section. Okay, so again, on a high level, going forward, I like I said in the beginning, I like to think about good principles for designing algorithms that are, I said, stable, but mostly focusing on privacy, that are private, and efficient enough to be practical. And I think a particularly interesting direction is in all these things that I have worked on and other people have worked on, we do the following. We say, find a differentially private algorithm that is always differentially private, but if your data are drawn from some distribution, it gives you the optimal error for that distribution. So a lot of the work goes like this. I think what would be useful, especially for practitioners, would be to drop the assumptions and so have an algorithm that automatically adapts to easier instances. So a differentially private algorithm that, again, is always differentially private, but its accuracy is optimal for the instance where your data are coming from, or what we call instance optimal. And so you don't have to say, oh, what do I think, what is the distribution that my data are coming from? What algorithm should I use for this? It's just a universally optimal algorithm.
And could you do this with, like, if you have checks for each, like the check that you have?
You could, yeah.
And then
you could check special cases.
Then do this one, check that one.
Yeah.
Do that.
Yeah, I still think it might be useful for practice if people had one thing to consider, one algorithm to sort of know, instead of a lot of different ones. But you could.
I mean, compilers can do this, right?
Oh, yeah. But I think a lot of my impression is that a lot of people who work with, like, social scientists, people who work with data, have a difficulty adopting private methods, not only like because of the lack of simplicity many times.
But that's the problem, is lack of tools, I guess. But
it could be.
You have a simple algorithm.
Yeah. I mean, on a high level, I think it's also just interesting on its own. We can do it in one dimension, but high dimensions are challenging for this problem. And we sort of made a little bit of an effort to adapt to the dimension in a recent work, but it's nowhere near the generality that we'd want it to be for this. So on a high level, I think practitioners would appreciate like something like instance optimal accuracy, and other tools that I think would be useful are uncertainty quantification tools under privacy, which we have quite like a much less of an understanding of what good principles look like there, like confidence intervals, things like that. And finally, social context. I think a disconnect between differential privacy and its use cases often is that people actually co-own data or trust people and don't trust others. And this social context is not captured exactly with the definition as is. It can be adapted, but in any case, we haven't studied algorithms for it. Okay, this is my privacy gist, but I want to take 5 minutes to mention, is this fine? Okay, 5 minutes to mention generalization. I think the only thing I want to say here is that, again, looking at connections between things is useful and exciting. What we did in that work was come up with a notion that we called conditional mutual information. Oops, sorry, I'll just flash this. Conditional mutual information of an algorithm. And all I want to say about it is that a lot of other conditions that imply generalization, and differential privacy is one of those, sort of are unified by this other notion called the conditional mutual information of an algorithm, which implies that the algorithm generalizes well. So the performance on nuancing data is close to the performance on the training data set. And this notion was actually a little bit inspired by differential privacy. It sort of uses this idea of swapping samples and not being able to tell that you did that. And it was later used on things that not only have to do with like excess risk and generalization, but it was used for privacy auditing. So notion for generalization came back to privacy to use like sort of a low computational overhead approach for privacy auditing. And it also characterizes the memorization accuracy trade-off. You know, large language models can memorize data points as they are. Can we figure out sort of ways to reason about this mathematically? And this conditional image information was used to that as well. So, you know, looking at all these things together, I think, again, just I want to point to the thesis that it's more like a research approach, I would say, not that I'm advocating for people to do research specifically on these, but like to be aware of other areas that use stability in other ways that can be beneficial for the thing that maybe you're looking at. I think framers like these can be useful for generalization when the data points are coming from a distribution that's not exactly the same as the ones in your training. And I think that's an interesting direction. And overall, I'd like to thank, I mentioned a bunch of works from people I've collaborated with, but mostly the restricted exponential mechanism was work with Gavin Brown, John Ullman, Adam Smith, and Marco Gabardi, and the robustness, differential privacy, connection, sort of equivalence was work with John Ullman and Hilal. Happy to take any questions or discuss any of the things on generalization, privacy, that you might be interested in. Thank you.
The application of that Gaussian estimation work that you did, where do you see it applied to improve the state of the art right now?
So yes, absolutely. So the question is, the work with the restricted exponential mechanism and the improved mean estimation technique, where can we see this applied to improve the state of the art? The big hope with all of these things and like looking at fundamental tasks in private statistics is that they would be used as better building blocks, I think, for other algorithms. And gradient descent is one of those things. So it could be, in principle, you could imagine replacing the averaging step in gradient descent, which is used for training large language models and not only just neural networks, replaced with better mean estimation algorithms. There are two.
There.
So
what would it do? So how would it work and what would it then potential benefit?
It could improve the accuracy, or I guess.
You wouldn't would you need to clip still?
No, maybe you wouldn't need to truncate. Yeah, you wouldn't need to clip. What I think is the difficulty, well, there are two things. One is, again, you'd need to kind of know the distribution that your gradients are coming from. And there, I don't know, that's maybe another reason instance optimality would be useful there. The second thing is, it is exponential time. We tried to sort of relax the Mahalanobis loss assumption, sort of requirement, and trade off like time with this affine invariant requirement. So we think about like Tukey depth not with respect to all the half spaces, but with respect to some of the half spaces, which would ruin maybe your accuracy, the shape of the error set, with the confidence set, which will ruin it with some probability, but it might still be accurate enough. So we've thought about this a bit, and we've implemented it and hope to see where it can go. In practice, one place it has been used is linear regression. Google came up with a paper, it's called Easy Linear Regression, which uses this approach, but they relaxed Tukey depth to only the basis. So instead of looking at all the half spaces to figure out the Tukey depth of a point, you'd look at the basis. And this gives you an error in a rectangle box. So this is like completely losing the affine invariant Mahalanobis. But still, it was sort of useful, and it gave faster and better accuracy algorithms for linear regression. I think they use it in pretty high dimensions as well. Yeah, so the hope is basically as a building block of things. Yeah.
In these cases where you have like data in higher dimensions, how useful and how computationally expensive is this whole approach with the Tukey depth computation? And
if you insist on using exact Tukey depth and computing the volumes exactly, it's n to the d squared. N is the number of samples, d is the dimensionality. This relaxation that we're thinking about, if you only use Tukey depth on like k half spaces, you don't look at all of those, then it's more like polynomial in k and d. So if maybe you're okay with k being roughly d, the dimension, this would be polynomial in d. And in practice, and there are some theoretical reasons for this, in practice, it looks like Tukey depth with d dimensions is actually close enough to exact Tukey depth for Gaussians, at least. And so this would be, if you had a polytope approximation, volume approximation algorithm, it would be polynomial time in d, and wait.
Some of those.
I think no, it's not bad. So okay, I think it's at worst 4.
And worst one, okay.
Yeah.
You're gonna ask me what constant?
Well, actually, our algorithm has really good constants. This is another reason why we really like it. So the Gaussian like noise has worse constants than ours. It's like 17. I think anything in like with 2 digits is a good constant. That's so it's a pretty good constant. But again, the time complexity is. Yes.
Just out of curiosity.
Yeah.
Does inverse sensitivity mechanism help to do this kind of?
Yes, you know many things. So the transformation from any robust to a differentially private algorithm is the inverse sensitivity mechanism, with like you try to approximate the output of the robust black box robust algorithm. The other way in which the inverse sensitivity mechanism helps and comes up is the instance optimal algorithms that we know for one dimension, because we don't know for high dimensions, but for one, is again the inverse sensitivity mechanism. So it is a promising approach. The reason it's blocked in high dimensions is because it does search. It is basically the exponential mechanism, and it searches over the whole d-dimensional space. D, the dimensionality comes up. And if you had an instance optimal algorithm, you'd want, instead of the dimensionality d, like the effective dimension of the data to show up. And the inverse sensitivity doesn't do it yet, as is. It's a really good question or direction. Thanks.
Yep,
Thumbs up.
All right.
Thanks,
thank the speaker again. Thank you, everyone.